So to reiterate, technically, if we were to select repeated samples of 36 respondents out of the target market and compute the mean willingness to pay or the sample mean for each sample, and construct a 95% interval each time, then approximately 95% of those intervals would contain the true population mean. Now, we don't know what the true population mean is. So we interpret this as saying that if we just take one sample, we are 95% sure that the confidence interval, in this case $27.82 to $29.38, contains the true mean or willingness to pay for this consumer product. So we need to look at this connection between the confidence interval, the true mean, and the individual values. We realize that the confidence interval estimates the mean. So if you want to know what specific individuals are willing to pay for this product, then I need to be careful when using the confidence interval created above. So let's take the lower limit, for example, as a conservative estimate. Note that this is the estimate for the mean of 36 people. So let's assume that the population mean is $27.80. Well, that's below our estimate. However, we note that this doesn't indicate that all people are willing to pay for this amount. It just means that it is what the average of all people would be willing to pay. So assuming that the population distribution is symmetric, then over half of the market will not pay this much. And then the opposite side of that is if the price is too high, $29.38, we estimate at the upper limit, and we price it very low, then we're leaving money on the table. So let's compare now and take a look at this relationship between our confidence interval and our error, and the sample size and the error. Now remember, what is the error? The error, if we take our sample mean plus and minus the error term, where the error is equal to our z-score times our standard error. So this is our error. So if I went to my boss and I said, we think that this product should be priced somewhere between $0 and $4,000, the error is so great that the sample that we've drawn really doesn't do us any good. We need to make sure that our error term is small enough that it has some relative value. Well, what we see here is as we increase our confidence interval, our error term increases. In fact, it increases asymptotically such that if we wanted to be 100% confident that the true population mean falls within our confidence interval, we would have to have an infinite confidence interval. So we draw the line, and most commonly it's drawn at about 95%. We recognize that we are going to be wrong 5% of the time, but we accept that because to be 100% confident, we would have an infinite confidence interval. Now, sampling takes resources, takes time, takes money. So we can see the relationship if we want to minimize the maximum likely error, the error term. We can increase the sample size, but it decreases significantly at first, but then the marginal benefit of increasing the sample beyond a certain point becomes negligible. So somewhere in this range, about 200 samples, we find that we're getting the biggest benefit for minimizing our error. So explain the relationship between the maximum likely error and the confidence interval. Well, these are directly related, meaning that the higher the confidence interval, the higher the error. So if I want to have a smaller error, I can accept a lower confidence level. What does this relationship tell us about the size of the confidence interval as we increase in confidence? Well, it increases. It increases positively, but not linearly, meaning that each point, if we move from, say, the 90% confidence interval to the 95% confidence interval, we can change our maximum likely error a small amount. But if we want to move from, say, the 95% confidence interval to the 99% confidence interval, our maximum likely error would change quite a bit. So explain the relationship between the maximum likely error and the sample size. Well, here is an inverse relationship, meaning that the larger the sample size, the smaller the error term. So what does this relationship tell us about how to select our sample size? Well, a small sample size can be benefited by increasing that sample by a little bit. We can reduce our error term. But once we get to a certain point, the marginal benefit of increasing, and I can't tell exactly where this is on the scale, but let's say it's 200. The benefit of increasing our sample from, say, 200 to 400 is not near as great as increasing our sample from 0 to 200. We can significantly reduce our error term by increasing our sample from 0 to 200, and then each additional sample gives us a lower marginal benefit.